Okay, hello everyone. Hello again, everybody. That was a rather long 10 minutes. I'm going to have to set a timer next time and kick people out. Or kick people out from asking questions. Okay, so a couple of things from the break. First of all, in terms of the lab exercises, labs, you'll notice there's the ones that are called pair, the ones that are called warm-up, and the ones that are called challenge. You have to do the ones that are called pair, and you have to do them with your lab partner. You can't do those by yourself. Like, do them with your lab partner. Those are the ones that you have to submit, and you have to do, and you get marks for. The challenge ones are optional. You can do them by yourself. You can do them with your partner. You can not do them at all. If you do them, you can submit them. You can do the auto tests and that sort of thing. But if they're too hard or you don't want to do them, don't do them. That's fine. You won't lose any marks for not doing them. And again, with the warm-up ones, you don't have to do them. So the ones that you have to do are the pair ones, and you have to do those with your pair. Does that all make sense? Hopefully? Cool. So if you've been looking at the challenge one and going, oh, this is really hard, I don't know what I'm doing, I'm going to lose marks, you're not going to lose marks. It's fine. Next thing. So something that I don't know if I've mentioned yet, but I probably should have mentioned. Guys, just shh. It's so effective to say shh, and be quiet. It's lovely. So something that I haven't mentioned, I think, that I really should have mentioned. One of the rules in this course is that you can't use any syntax in your lab or assignment or anything, exercises, until we've seen it in lectures. So if you already know how to do something fancy in C, but we haven't covered that in lectures yet, you can't use that in your labs. You can't use that in your challenge submissions. You can't use that in your assignments. A lot of the challenge exercises are really, really easy if you know about all these fancy C things. Well, not really, really easy, but they're a lot less challenging. So that's one of the reasons why you can't use anything we haven't seen in lectures. But it also just sort of narrows the playing field. Like, I mean, that's one reason, but also, I don't know, there's lots of reasons. I think it's good for you to all sort of get a foundational learning and to learn everything kind of from the bottom upwards. So maybe you already know some fancy C things, but maybe you know those instead of some of the basics, or maybe you use those instead of understanding if statements really well. So I think it is important that you definitely can do all of the, all the things we cover in this course. But another thing, when we ask you to do an addition calculator, we don't actually care that you can add numbers together, because you could just go to a real calculator and add numbers together, right? The goal is for you to practice doing something to build this yourselves. If all I wanted was a working calculator, I'd go buy one from the store, or I'd go to Google. So when we set exercises, even if you know some sneaky way to do them, that's like, fancy, I don't know, magical, C++, whatever stuff that we haven't covered. The point of the exercise isn't to make a calculator, it's for you to learn the skills and practice the skills and use those to make a calculator. Cool. And one more thing. So how many of you watch the lecture videos? Do watch them, would watch them, might watch them? Okay. So for both of you who do and don't watch them, if I sent out an email when the videos had been uploaded, would that be really annoying or really useful? Raise your hand if that would be really annoying and you would hate me if I did it. Okay, so you guys can set up an email filter that goes, when Andrew sends an email saying lecture videos are up, it'll delete it. But I know that they will be up as soon as they can be, which on Monday was like 8 o'clock at night because I had to go through and fix up the second video. So I want to make sure that everybody who wants to watch them can watch them when they're up. And if it'd be helpful, I want to tell you, hey, the videos are up now, you can go watch them. So maybe I'll send that out when I do today's videos, and if it's really annoying and you hate it, then you can just archive it. Although I'm sure you probably all get so much email that one more email won't make that much difference. Cool, and finally, I will upload all of the code the tutors have written today if they're okay with it. I assume if I take their names away, they'll be fine with it, because I did ask them to write bad code. Cool, okay. So moving on to looking at numbers. So this joke brought to you by that tutor who makes puns. So thinking about number system, thinking about numbers. If I say the words base 10, how many of you know what that means? Okay, basically all of you. Basically all of you, ha ha ha. I thought you had a class. Why are you still here? Okay, he writes the puns. So base 10 is sort of what you would refer to as normal numbers, right? We count from 1, 2, 3, through to 9, then 10, then 11, then 12, then, 20, 30, and so on. And then we can go up by 1 and we can get to like 1,000,000. And that might seem like that's all that numbers are, but there are other bases like base 60, for example. If you think about the time it is, it's currently 5:38, right? Eventually it'll become 5:59, and then it'll become 6 o'clock. There's no such thing as 5:60 or 5:61. Like when we hit the minute after 59 minutes, we go back around to the first minute of the next hour. And we could refer to that as base 60. Fun fact. And similarly, base 12, the hours of the day, or base 24 if you do 24-hour time. Like you wouldn't say, 11, 12, 13 p.m., 14 p.m., 15 p.m. You might say 1400 if you mean 2 p.m. and 24-hour time. But then you'd go like 2300 is 11, but you wouldn't say 2400 is, because the hours cut off at 23. So hopefully that kind of makes sense. We have, numbers don't just always go from 0 to 9 and then 10 to 19 and so on. Sometimes we have weird cutoffs in numbers, like, minutes, we end at 59, then we go to the next one, the next hour. Why is this relevant to computers? You'll find out soon. So thinking to computers, computers work in two-state logic. Computers are on or off, right? The fundamental hardware building blocks of computers are basically things that can say either I am on or I am off, and lots of those all combined together. Yeah, and that's easy if we can do something like have our logic gate or have high or low voltage levels. So we often use bases that are powers of 2. So we've got binary. How many of you have heard of binary? I guess how many of you have not heard of binary? Yeah, so binary refers to like zeros and ones, right? And you often see like binary code associated with computers and it's like written in green font on a black background and there's like a hacker. Yeah. So binary just refers to numbers that are either 0 or 1, or numbers that are made up of a series of zeros and ones. Are you leaving? Am I that bad? Why are you even at the lecture? He's one of the tutors. I hope. I hope you're not someone who just looks like the tutor. Cool. So binary base 2, zeros and ones. More on that in a second. So in computing, we use a lot of binary. We often talk about base 8, which is called octal, or base 16, which is called hexadecimal. So before we talk about kind of how to think about those other bases, let's think about how decimal numbers work, how the base 10 that we're used to works. So when we say something like the number 4,705, you all know what that means, right? You know that it's a number that's 4,705 big. And you might have, when you were learning numbers back in primary school, learned that you've got like the ones column and the tens column and the hundreds column and the thousands column. So this number here is 5 lots of 1, plus 0 lots of 10, plus 7 lots of 100, plus 4 lots of 1,000. And that's what we've got written down here. We've got 4 lots of 10 to the power of 3, which is 1,000. 4 lots of 1,000, 7 lots of 100, 0 lots of 10, and 5 lots of 1. So yeah, we refer to that as the base of this number is 10, or the radix is 10. It's the same as base. So in each spot, we can have digits 0 through 9. So, when we're counting numbers, we have 0, 1, 2, 3, so on 9. And then we hit 9, we've run out of numbers, and we go to 10, which is 1, 0. And each place that we have has a value of 10 to the power of n. So what that means is kind of going from right to left. Maybe I'll grab the document camera. Can I use Microsoft Paint without it being ridiculous? I don't think I'll do a very good job because I'm drawing with a mouse, but we'll see. So we had the number, was it 4705? Right, and so we said that that was 5 lots of 1, 0 lots of 10, 7 lots of 100, and 4 lots of 1,000. Can you read my handwriting? And so this is like the ones column, the tens column, hundreds, thousands column. But the number 1 is equivalent to, why did that get smaller? 10 to the power of 0. 10 is 10 to the power of 1. 100 is 10 to the power of 2. And 1,000 is 10 to the power of 3. So does this make sense? This number here is the number of 10 to the power of zeros we have to the number of 1s. This is the number of 10 to the power of 1s, or the number of 10s we have. The number of 10 to the power of 2s, or hundreds we have, and 10 to the power of 3s, or thousands we have. I apologize for the terrible Microsoft Paint drawing. Cool. And we can write numbers with the base or the radix. Okay, with the base or the radix as a subscript, so like the number and then base 10 with 10 down the bottom in smaller writing. Cool, and so binary numbers are done in a similar way. Rather than being this many lots of 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, we look at powers of 2. So base 2 binary, this number here is the number 2. So I've written down here, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. And so this binary number here, 1, 0, 1, 1, is saying that we have one lot of 8, we have no lots of 4, we have one lot of 2, and one lot of 1. If we add those together, we've got 1 times 8, so 8, plus 0 times 4, plus 1 lot of 2, so 8 and 2 is 10, plus 1 lot of 1 is 11. So that would be equivalent to the number 11 in base 10, or in normal numbers. Cool, and here are some powers of 2. It's useful to recognize these numbers, I guess, so looking at them and going, oh, that's a power of 2, because they'll come up a lot in computing. I recommend, if you're a person who can learn numbers, it's useful to just know these. So, you know, 1, doubling 1 is 2, doubling 2 is 4, doubling that is 8, 16, 32, 64. Up to 1,024, it's as many as you need to know. But this is just them all written out here. It's exponential. So we can convert binary numbers to decimal numbers sort of like I did before. The number 1011 means we've got one lot of, this is in the, actually let's start from this side. So this is in the rightmost column. So that's the number of 2 to the power of zeros we have, or that's the number of 1s we have. So we've got one lot of 1. Then this one here across here is the number of 2s we have. We've got one of those. This is the number of 4s we have, which is none. And this is the number of 8s we have. So we can turn that into 1 times 8, plus 0 times 4, plus 1 times 2, plus 1 times 1. So then 8 plus 2 plus 1 gives us 11. Does that make sense so far? Are there any questions? 2 thumbs up? Must be doing a good job. Cool. And so doing decimal to binary, you kind of do the same thing but in reverse. And this is where knowing your powers of 2 comes in handy. So if we wanted to turn the number 221 from decimal into a binary number, the first thing we want to do is work out what's the biggest power of 2 that we can get out of this. And so if you know, or if we go back to our table, 221 is smaller than 256 and it's bigger than 128. So the first thing we want to do is we want to take this number and subtract out 128. So we know that our number is going to be 1 times 128, which was 2 to the power of 7. And then we've got like 101 left over. So then we take our 101, we subtract the next smallest power of 2, which gives us 64. So we know there's going to be 1 128, 164, and then the leftover part is 37. And we continue going along for each of the powers of 2. So I'll kind of draw them here. This is 128, which was 2 to the 7. 0, 1, 2, 3, 4, 5, 6, yeah, 2 to the 7. 2 to the 6 was 64. We have one lot of 64 in there. Then we had 37 left over. We can get a 32 out of that, so we have a 32 there. Then that gives us 5 left over. This one was 16. We can't do 5 minus 16 and still have a number left. We can get a 4 out of that, and then we can get a 1 out of that. So hopefully that sort of makes sense. Subtract out the powers of 2, and then for each one where you did manage to subtract that one, put a 1, and otherwise put a 0. Cool. I'll skip over octal for a second. So then we also have hexadecimal numbers, and so decimal numbers, normal numbers are base 10, binary numbers are base 2, and hexadecimal numbers are base 16. So you know how before I said that we have decimal numbers which go from 0 to 9, and then we run out of numbers? We run out of digits. What do we do about the remaining digits? Like if we want to represent more than, yeah, A, B, C, D, E, you said. So if we want to represent more digits than we have, we want to somehow go 0, 1, 2, 3, and so on, and then get to 15, but still with one single character. We just go and use the first part of the alphabet for that, because we can. So when you count in hexadecimal, you count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then instead of going to 10, you go A, then you go B, C, D, E, F, and then we get up to 1, 0, which is 16. So I'll say that again. We go 0 through 9 are the same things. Then when we get to 10, instead of saying 10, we say A. Instead of saying 11, we say B, and so on through to F, which is 15. And so just like before, each of these, each of the columns, I guess, in our number, we've got this number. So if we've got 3AF1, this is the number of 16 to the power of zeros we have, the number of ones. The next one across is the number of 16 to the power of ones we have, it's the number of 16s. And this becomes the number of 16 squared, so the number of 256s. And this is the number of 4096s we have. And so we can calculate this again like this. So we have, starts with 3, so we've got 3 lots of 16 to the power of 3. This one's A, which was 10, so we've got 10 lots of 16 squared. This one was F, which is 15. 15 lots of 16. And then this is a 1, so we've got 1 lot of 1. And so if we added all those together, we would get 15,089 in base 10. Does it make sense so far? No? Which part did make sense? That's understandable. Let me try again to get this working. So let's look at this some more. I had some confusion up the front. Would you say your first confused thing was why there were letters? Was that a confusing thing? So if you think about base 10, right, we have 10 different things we can use to represent numbers. We have the digit 0, and then we have the digits 1 through 9. So that's 1 through 9 is 9 things, plus 0 is 10. And so when we have binary, base 2, we have 2 different things. We have 0 and 1. So if we want to do base 16, we need to have 16 different things that we can use to represent the letters, to represent our numbers. And so because we only have 10 digits, 0 through 9, because we want to have 16 different values,